Welcome to the lecture on transmission line theory. In this lecture, we will study how to determine primary and distributed constants of a line, propagation and attenuation constant, phase constant of a line, characteristics and input impedances of a line, standing ratio and reflection coefficients of a line. You know that lines are used for power transmission, telephone transmission, and traces on printed circuit boards, traces on multi-chip models, traces on integrated circuit packages. If the line is not properly terminated or if the input impedance is not equal to the characteristic impedance, then you will get the reflection, and also you will get different values of attenuation and phase constants. So we know that the transmission line equations of voltage and currents is given by Vz is equal to Vs e raised to minus gamma z plus Vr e raised to plus gamma z e raised to j omega t. So Vs e raised to minus gamma z gives the sending voltage and Vr e raised to plus gamma z gives the reflected voltage. Similarly, the current Iz is given by Is into e raised to minus gamma z. This is the sending current plus IR e raised to plus gamma z is the reflected current. So into e raised to j omega t, this is variation in the time. So impedance Z is given as R plus j omega L. This combination of inductance and resistance in the series arm, and admittance is given in the shunt arm. It is given by conductance plus the capacitor reactance j omega c. Characteristic impedance Z0 is given by under root of the impedance divided by admittance of a transmission line, and propagation constant gamma is given by under root of impedance into admittance of a transmission line. This is also equal to alpha plus j beta, where alpha is attenuation constant and beta is phase constant. For lossless line, so there is no resistance and no conductance, therefore R is equal to 0, G is equal to 0. And for low loss line or distortionless line, we will get the condition RC is equal to LG. Therefore, gamma is equal to j omega under root of LC if and alpha is equal to 0, beta is equal to omega under root LC, and Z0 is equal to under root of L by C for a lossless line. And for low loss line or distortionless line, gamma is given by under root of Rg plus j omega under root of Lc. Therefore, alpha attenuation constant is equal to under root of Rg, and the phase constant is given by beta is equal to omega under root Lc, and Z0 is equal to ratio of under root of L by C, R is equal to under root of R by G, and Z input is equal to input impedance is given by VL divided by IL is equal to Z0 into bracket ZL plus Z0 tan hyperbolic gamma L over by Z0 plus ZL tan hyperbolic gamma L, and reflection coefficient K is given by amplitude of the reflected wave divided by amplitude of the incident wave. This is given by load impedance minus characteristic impedance divided by load impedance plus characteristic impedance. And voltage standing ratio is defined as maximum amplitude of the signal to the minimum amplitude. This is given by 1 plus reflection coefficient divided by 1 minus reflection coefficient. And input voltage V in is given. This is equal to Vg into Zg divided by Zg plus Zin, where Zg is the generator impedance. Zin is the input impedance of the line. Phase velocity Vp is given by omega divided by phase constant beta, and wavelength lambda is given by Vp by f or 2 pi by beta, and phase constant beta is equal to 2 pi by lambda. We'll solve one problem to find the that is standing wave ratio, reflection coefficient, and characteristic impedance. So at a frequency of 4 MHz, a parallel wire transmission line has the following parameters. R is equal to 0.025 ohm per meter, L is equal to 2 microhenry per meter, G is equal to 0, C is equal to 5.56 picofarad per meter. The line is 100 meters long, terminated in a resistance of 300 ohm. To find VSWR and reflection coefficient at load. If given here a length of the line is 100 meters, R is equal to 0.025 ohm per meter, L is equal to 2 microhenry per meter, equal to 2 into 10 raised to minus 6 Henry per meter, G is equal to 0, C is equal to 5.56 pico nanofarad per meter, and ZL is equal to 300 ohm, F is equal to 4 megahertz, is 4 into 10 raised to 6 hertz. Therefore, the characteristic impedance is given by Z0 is equal to under root of Z by Y. We substitute ZL is equal to R plus J omega L and Y is equal to G plus J omega C. We'll get 0.025 plus J into 2 pi into 4 into 10 raised to 6 into 2 into 10 raised to minus 6 whole divided by 0 plus J 2 pi into 4 into 10 raised to 6 into 5.56 into 10 raised to minus 9. So if we simplify by using rectangular to polar coordinate using calculator in the numerator and denominator and dividing the values numerator by denominator, we'll get Z0 is equal to 600 minus J into 0.149 ohm. Then by knowing the value of Z0, we can calculate the reflection coefficient. This is given by ZL minus Z0 divided by ZL plus Z0. ZL is 300. So Z0 is 600 minus J 0.149 if we substitute here. In the denominator also 300 plus 600 plus J into 0.149. Again, you have to convert rectangular to polar coordinate the numerator terms and in denominator terms and divide. And after dividing again, you have to convert polar to rectangular coordinate. You will get minus 0.333 plus J into 0.11 into 10 raised to minus 4. And what is standing wave ratio is given by 1 plus magnitude of K divided by 1 minus magnitude of K. This is equal to take magnitude of this value, therefore under root of 0.333 square plus under root of 0.11 to 10 raised to minus square. Simplify, you will get here K is equal to 3, therefore you will get 1 plus 3 divided by 1 minus 3, 4 by 2 is equal to 2. And next problem, here we can find the constant of a line given characteristic impedance is equal to Z0 is equal to 50 ohm, attenuation constant alpha is equal to 0.00115 upper per meter and beta is equal to 0.8 radians per meter. You have to find the primary constants RL, GC or distributed constant per meter of RL, GC. Given Z0 is equal to 50 ohm and alpha is given, beta is equal to given and F is given as 100 megahertz is equal to 100 into 10 raised to 6 hertz. Substitute Z0 is equal to under root of R plus J omega L with G plus J omega C. We will get some value. And for lossy transmission line, Z0 is equal to under root of L by C as RC is equal to LG. Therefore, root of L is equal to Z0 under root C is equal to 50 under root C and alpha is given by that is equal to R into under root of C by L. Therefore, beta is equal to omega under root LC. Then roots C from this is given by beta divided by omega root L. Substitute the value, we get 0.85 divided by 2.100 into 10 raised to 6 under root L. From 192, we get root L by 50 is equal to 0.85 divided by 2.10 raised to 8 root L. Cross multiply, we get L is equal to 0.8.21050 whole divided by 2.10 raised to 8 is equal to 0.2 microhenry. Therefore, C is equal to L by 50 square. This is equal to 0.2 into 10 raised to minus 6 divided by 2500. This is equal to 80 picofarad. So from alpha is equal to R root C by L and R is equal to alpha root of L by C. You can calculate R is given by alpha is 0.00115 under root of L is 0.2 microhenry divided by C is 80 picofarad. Substitute and simplify. We get 0.00115 into 10 raised to 3 under root of 2 by 800. Therefore, R is equal to 1.115 into 1 by 20 is equal to 0.0576 ohm. But RC is equal to GL, therefore G is equal to RC by L. Substitute the value of R and C whole divided by L. And simplify, we get 23 micromole. Therefore, the values of R are 0.0576 and G is equal to 23 micromole and C is equal to 80 picofarad and L is equal to 0.2 microhenry. So problem number 3, a transmission line operating at 125 MHz has Z0 is equal to 40 ohm, alpha is equal to 0.02 Nepar per meter and beta is equal to 0.75 radian per meter, and you have to find the line parameters RL, GC. Here the frequency given is 125 into 10 raised to 6 Hz and the characteristic impedance Z0 is equal to 40 ohm and attenuation constant alpha is equal to 0.02 Nepar per meter and the phase constant beta is equal to 0.75 radian per meter. Since Z0 is real, therefore there is no reflection and given attenuation constant not equal to 0. Since the Z0 is only real part, therefore the line is distortionless. Therefore, the formula for phase constant beta for a distortionless line is given by omega under root of LC and Z0 is equal to under root of LC. Multiply equation 1 and 2, we'll get omega into L is equal to beta Z0. Therefore, L is equal to beta Z0 by omega. Beta is 0.75, Z0 is 40, whole divided by 2 pi of 2 pi into 125 into 10 raised to 6. If we simplify, we get inductance is equal to 38.2 nanohenry per meter. And from 2, we get C is equal to L by Z0 square. So L is 38.2 into 10 raised to minus 9 and Z0 is 40. Z0 square is equal to 40 whole square. This is equal to 23.9 picofarad per meter. From alpha is equal to under root of RC and RC is equal to LG, we get R is equal to under root of RG into under root of R by G is equal to under root of RG L by C. This becomes alpha into Z0. Therefore, if you substitute, this will get 0.8 ohm per meter. Therefore, G is equal to alpha square by R as alpha is equal to RC is equal to LG. From A, R is equal to alpha Z0 is equal to alpha L by C alpha R by G. R is equal to this one. Therefore, G is equal to 0.5 millimole per meter. Therefore, R is equal to 0.8 ohm per meter and L is equal to 38.2 nanohenry per meter. C is equal to 23.9 picofarad per meter. G is equal to 0.5 millimole per meter. So, problem number 4. here a 100 kilometer telephone line has a series resistance of 40 mega ohm per kilometer and inductance of 3 millihenry per kilometer at an omega is equal to 5000 radian per second. At ascending end there is a generator supplying 100 volts peak at 5000 radian per second in series with a resistance of 300 ohm. The load at the receiving end consists of a 200 ohm resistor. If C is equal to 0.015 microfarad per kilometer and G is equal to 1 microsecond per kilometer, find the voltage and current as a function of Z and calculate their values at the midpoint of the line. The load current is IL is equal to minus 0.115 plus 10.0268 ampere. Therefore, given here R is equal to 4000 ohm per meter, L is equal to 3 into 10 raised to minus 6 Henry per meter, G is equal to 1 into 10 raised to minus 9 Siemens per meter or mho per meter, C is equal to 1.5 into 10 raised to minus 11 farad per meter. Therefore, omega is equal to 5000 radians per second and Vs is equal to 100 volt and Rs is equal to 300 ohm. L is 1 into 10 raised to 5 meter and IL is equal to 0.115 plus J into 0.0268 ampere and ZL is equal to 300 ohm. IL is equal to minus. Therefore, Z0 is equal to under root of R plus J omega L divided with G plus J omega C. This is equal to 1673 minus 1590 J. And gamma is equal to under root of R plus J omega L, G plus J omega C is equal to 451 minus J 56.1. This is solved by substituting the value of R omega L and G omega C and converting rectangular coordinate to polar coordinate, and after finding the value you have to reconvert polar to rectangular. The voltage and current along a lossless transmission line is given by Vz is equal to V0 plus e raised to minus gamma z plus V0 minus e raised to plus gamma z and Iz is equal to V0 plus divided by Z0 e raised to minus gamma z minus V0 minus Z0 e raised to plus gamma z. At load end of the transmission line RL, IL, we have Vz is equal to 0, we get ZL, IL is equal to V0 plus V0 minus, and I at Z is equal to 0, we get IL is equal to V0 plus minus V0 minus whatever Z0, equation number 5, 6. Adding and subtracting equation number 5 and 6, we get V0 plus is equal to IL by 2 into bracket ZL plus Z0 and V0 minus is equal to IL by 2 ZL minus Z0. We substitute the value of ZL, Z0 and IL in equation number 7 and 8. We get V0 plus is equal to minus 36.7 plus J into 12 and V0 minus is equal to 13.7 minus J 6.6. Substituting V0 plus and V0 minus in equation number 3 and 4, which describes the transmission line voltage and current as function of Z. Therefore, at L is equal to L by 2, we will get V Z is equal to L by 2 is equal to minus 15.9 minus J 58 and I at Z is equal to minus L by 2 will get 3.7 minus J 82.9 milliampere. By substituting V0 plus V0 minus and Z is equal to minus L by 2 in equation number 3 and 4.